In this section, we'll talk about a one sample t confidence interval, and we use this when sigma, or our population standard deviation, is unknown. So suppose we have a simple random sample from a normally distributed population, but we don't know the population standard deviation sigma, which this makes sense, right? Because we never have we rarely have our population data. And so why would we know our population standard deviation sigma? There's a few scenarios where that actually makes sense, but in practice, usually if we don't know the population mean, we don't know our population standard deviation. But what are we going to do? Because all of our formulas so far use sigma, our population standard deviation. So what we will do is we estimate our population standard deviation sigma with our sample standard deviation S. That makes sense, right? If you don't know your population standard deviation, estimate it with your sample standard deviation. When we estimate it with our sample standard deviation, we switch from using a normal distribution to what we call a t-distribution. So if our original sample population is normally distributed, then for any sample size n, the sampling distribution of, if we do x bar minus mu over s over square root of n, is what we call a t-distribution with n minus 1 degrees of freedom. So the t-distribution is very, very similar to our standard normal distribution, our z-distribution. It's bell-shaped and symmetrical. The graph is centered at 0, so you can see kind of what it looks like here. It kind of looks like a bell shape. It's centered at 0, it's symmetrical. The t-distribution, though, is more spread out or has more variability than our standard normal distribution, our z-distribution. The shape of our t-distribution depends on our degrees of freedom, which we call df. So you'll see here, this orange line is 1 degree of freedom. It has a lot more area in the tails. Then we have 2 degrees of freedom is this purple, 5 is the blue, and black is infinite degrees of freedom. Okay, so you'll notice what happens as our sample size increases. Well, I guess I haven't actually told you what our sample size is, but as our degrees of freedom increases, because that's related to our degrees of freedom. Oh, no, it does say it here. Notice here our t-distribution has n minus 1 degrees of freedom. So degrees of freedom equals n minus 1. So as n gets bigger, our degrees of freedom get bigger. So as our sample size increases, the t-distribution gets closer and closer to the standard normal z distribution. We also introduced something called our standard error. So since our theoretical standard deviation of x bar is the sigma of x bar equals sigma over square root of n, we estimate the standard deviation. So not only are we estimating our population mean, but we also have to estimate the standard deviation with an s over square root of n instead. This is called our standard error of our sample mean, or we could write SE for standard error of x bar is equal to s over square root of n. Our standard error is a way of describing how accurate our sample mean will be at estimating our population mean. So smaller standard error means your estimate will be more accurate or more precise. So smaller standard error means your estimate of the population mean is more likely to be accurate. Okay, so our one sample t confidence interval. Again, we are going to use this when we don't know our population standard deviation. So we use this when we know a sample standard deviation. So know our sample standard deviation. Let's capitalize that sample. So our one sample t confidence interval from u is going to be x bar plus or minus t star times s over the square root of n. So instead of a z star, we use t star. We have n minus 1 degrees of freedom, and notice we would just find t star means you have the 95% or whatever your confidence level is area inside our t distribution. Now, conditions to use this is your population is normal or n is at least 30. Now, if you don't know if the population is normal, you can just check to see if your sample data looks normal, because if your sample data looks normal, the original population was probably normal as well. We're not actually going to do these by hand though, we're going to use our calculator. So in either calculator, we're looking for something that has like a t confidence interval. We're also dealing with just one sample, because that's all we've learned how to do yet is one sample. Now, just as a remark, because our standard normal table was so much easier to use than a t-table. Now again, we're not using tables in this class, but people used to use them. And the z-table is so much easier than the t-table. So many books would suggest that if n was at least 30, just use the z-table because it'd be pretty close to the same. And they often say just use the z-confidence interval, again, if n was greater than 30, because it was just easier to use. But we have calculators now, so you may as well use the correct t-values and the correct t-confidence interval. Besides being theoretically correct, in practice, I've never seen anyone switch and just use the z-confidence interval when they should have used t. Okay, so the correct way to make your decision about which confidence interval to use is we use z when we know the population standard deviation sigma. We use t when we know the sample standard deviation s. And this is going to hold for the next couple chapters as we move on to other things. Z is always for a population standard deviation, and t is when we have a sample standard deviation. So let's try an example. Remember, we had a car mileage case from previous sections. We found a sample of 50 mileages. Now, as you're doing problems, write down what they tell you. N equals 50. We had a mean of x bar equals 31.56 and a standard deviation of s equals 0.7977. Okay, first, do we need to check to see if the sample looks normally distributed? Well, in our case, we have a large sample size, so n is bigger than 30. So it doesn't matter if the data is normal, because it either needs to be normal or a big sample size, and we have a big sample size. Okay, next, let's find a 95% confidence interval for our population mean mileage mu of our new mid-size model. And let's interpret this confidence interval. So we could use a formula, but we don't have to in this class. We're just going to plug it straight into our calculator. So we'll use our calculator. We want to use a t confidence interval. Okay, so let's pull up our calculator. So this is a little bit different than what the other things we've been doing. Okay. We need to find our stat menu first. So here's stats. We want to go over to test. They put it under test, you know, it's called a confidence interval, and go down until you see a t interval. You might also notice there's a z interval, and you might figure out, oh, everything we did by hand in the last section, we could probably do with our calculator. That is true. It's good to practice some things by hand, but if you want to switch and use your calculator now, you can. But right now we're interested in a t interval. So enter. Okay. Now you can choose between putting your input as data or stats. We're going to do stats because we just have all the summary statistics. Our sample mean is 31.56. Now, SX, that's our standard deviation for our problem, our sample standard deviation, so 0.7977. My sample size was 50. Put in your confidence level. We want a 95% confidence level, so it already has it in there as a default 0.95. Now, I think both of these calculators, you can either put 95 as a percent, or you can do 0.95. Either way is going to give you the correct answer. And it looks like my interval is 31.333 to 31.787. So that's a pretty precise narrow interval. We're pretty sure it's 31 something there, aren't we? And anytime you find a confidence interval in my class, you have to interpret it. So we are 95% confident that the population mean is going to be inside that interval. Okay, so we're 95% confident that the population mean for gas mileage for all the cars is between 31.333 and 31.787. So again, that's a pretty precise narrow confidence interval. I think I'd be fairly confident telling anyone it's around, it's about 31 miles per gallon or 31.5 miles per gallon. So you can try the next one on your own. Then you'll also find sometimes I just give you computer output instead of even using it on your calculator. So let's try this example. One measure of a company's financial health is its debt to equity ratio. One bank wants to make sure that its mean debt to equity ratio is less than 1.5. To estimate the mean debt to equity ratio of the current accounts, the bank randomly selects a sample of 15 of its accounts. So we have n equals 15. Here's the actual data, if you want to study that. And notice now I'm giving you some graphs. Okay, that's good to be able to look at our data and see what it looks like. Okay, here's a box plot. You can see from the box plot that the box is fairly symmetric. There might be one possible outlier. The histogram, it looks fairly symmetric. Again, kind of that possible outlier. It doesn't really look that much like an outlier to me though. And our normal curve plot looks fairly close to a straight line, which means the data is normal. So this data doesn't look exactly normal, but it's really not very bad, especially for a small sample. We don't expect our data to look exactly normal because it's such a small sample size. So I would say my data looks normal enough. Really, this is a pretty good data set for it looking normal. So even though I have a small sample size of just 15, so sample size of 15 is small, but the data looks normal enough. So we can go ahead and do our procedures. Then I also gave you descriptive statistics. Notice there's the count of 15. That's their way of saying n equals 15. The mean, x bar equals 1.3433. You have sample variance. That would be s squared equals 0.0369. And sample standard deviation S equals 0.1921. Notice it gives you here a 99% confidence interval. So we have a 99% confidence interval of 1.19 to 1.49. So I don't even have to really do anything because I can just put it in my computer and now you can just read it straight from the output. And last, this half width, when they say half width, that just means margin of error, is 0.1476. Okay. So to find a 99% confidence interval, well, that was pretty easy. It was 1.19 to 1.49. And to interpret it, again, the short thing would be 95% confident that population mean is in the interval. Now let's put it in context. Let's read again. Okay, so we're talking about debt to equity ratio. So the average debt to equity ratio for all the accounts. So we are 99% confident that the average debt to equity ratio for all the accounts is between 1.19 and 1.49. And what does that 99% confidence level mean? It means of all the possible samples we could have chosen, each sample would give us a different sample mean, and that means a different confidence interval. Of all those confidence intervals, about 99% would actually contain the population mean mu. Okay. Now, just to come back and look at this problem again, they said they want the debt to equity ratio to be less than 1.5. Looking at our confidence interval, does our confidence interval seem like it's less than 1.5? So our confidence interval of 1.19 to 1.49 is less than 1.5. So I feel fairly confident in saying the mean debt to equity ratio is less than 1.5, so they should be happy. Okay, there's one more problem for you to try here. Again, I gave you the computer output, so you get to save some time there. And one more example for us. What if we have a data set for one person and the number of hours they spend per week on homework? So here's our data set, and let's find a 90% confidence interval for the average time per week for all of these. But notice here, n is only 1, 2, 3, 4, 5, 6, 7, 24. Okay, so this is a small sample size. So we need to check if data is normal. Okay, looking at this, the normal curve plot, this would be a straight line. That is not a straight line. Okay, my box plot, notice it is obviously not symmetric. I don't have two halves of the box that are the same, so this one is not symmetric. And notice it's not just a small possible outlier in between the two dashes, it's lots of outliers. Or at least 3 outliers, which is a lot in statistics. And looking at my graph, it is not normal, or my histogram. Definitely not normal. It's very right skew. And you can see those outliers again. So there's outliers. So this data is not normal. So the data is definitely not normal. Okay, so we can't find a confidence interval for this data because it is a small sample and the data is not normal. Okay. So if our sample size is small and our sample population is not fairly bell-shaped or normal, we can't use our normal distribution or the t-distribution. In this case, we'd use what's called a non-parametric method. We won't talk about in this class, but they are out there.